We began our story with a neural network, a binary classification model where we want to input images, and upon running them through the model, we want to classify whether the output is of class A Lambo, or class B, a Ferrari, where we give a score of 0 or 1 respectively. And let's say we were to input 1,000 images. Of them, 500 are Lambos and 500 are Ferraris. And after running them through the model, of the 500 Lambos, let's say the model predicted 348 of them to be Lambos, and of the 500 Ferraris, the model predicted only 429 to be Ferraris. Well, given these findings, how can we organize them in such a way that we can extract more information and insight about how the model is performing? Well, one way to start is we can generate a 2x2 contingency table, where the idea is that the rows represent the reality, what the images actually are, and the columns represent the predictions, what the test outcomes them as. And right away, we can see that 348 belongs to the top left. Because of the actual 500 Lambos, the model predicted 348 of them to be Lambos. And similarly, 428 belongs to the bottom right, because of the 500 Raris, the model predicts 429 of them to be Raris. Each row has to add up to 500, so by that we can get the remaining cells, 71 and 152. And from this we can sum both columns, so we get 419 for the predicted Lambos and 581 for the predicted Raris. Now, these are just numbers on a screen. How can we add meaning to each of these cells? Well, one way we can think about it is like this. We can ask ourselves two questions. For each outcome, are they positive or negative? Positive or negative just means are they of one class or the other. In our case, positive is for the Lambo class and negative is for the Rari class. And the second question we can ask is, are these outcomes true or false? Meaning, does that positive or negative truly reflect the reality? So given this approach, let's start with the top left. We say that this one is a true positive because, answering the first question, the model predicts it as a Lambo, a positive, and it truly predicts it because it actually is a Lambo. Moving to the right, we get a false negative because the model predicts it as a negative, a Ferrari, but it falsely predicts this because it is actually a Lambo. And similarly, we can get false positive. It falsely predicts a Lambo when it is a Ferrari, and a true negative. It truly predicts a negative. It is a Ferrari. Okay? Now further, one quick tidbit. If you add the top row, you get the actual positive, all the Lambos. If you add the bottom row, you get the actual negative, all the Raris. And if you add the left column, you get the predicted positive, the predicted Lambos. And if you add the right column, you get the predicted negative, the predicted Raris. Now, based on these rows and columns, you can even further get the total sum in two ways. You can get the total sum in terms of the columns, or the total sum in terms of the rows. We start with accuracy, which is all the correct predictions out of the total predictions. So the more correct predictions you have, the more accurate your model is. So let's use a subsample of 6 images. And let's say the model predicts each images as such. Okay. Now, if you go through each of these one by one, we can say that for the first one, the model correctly predicted a Lambo. It is a Lambo. For the second one, it correctly predicted a Rari. It is a Rari in the image. For the third, it messed up. It incorrectly predicted a Lambo, but we see a Rari in the image. And so on and so forth. Correct, incorrect, and correct. Okay? And given just this subsample, we can say that the accuracy is 4 correct predictions out of the total 6. So an accuracy of 66%. Okay? Now, saying this in terms of the table, all the predictions, the denominator is the total table, but the numerator, the correct predictions, are just the true positive and the true negative, because that is when the test is right, when it truly predicts them. Putting this together into an equation, we get TP plus TN over S. Next, let's take a subsample of 20 images instead, where we say that the model predicts the yellow as Lambo, and the red as Rarries. And of these, let's just focus on the positive, the Lambo predictions for a moment. Of these positive predictions, let's extract the ones that are actually Lambos in the numerator. In terms of the table, we say that the denominator is the true positive over the false positive. Remember, this column is the positive predictions, the Lambo predictions, so positive predictions. And the numerator is the true positive, where the model actually picked up a positive, these ones. These are actually Lambos. Putting this together into an equation, we have the following. And this is what you call precision. How precise is our model at predicting the positives? The higher this value, the more precise our model is as correctly predicting the positives. Now let's get back to our subsample, and instead of focusing on the positive predictions, let's actually just focus on the positive images, the images that are just Lambos. So we have these, and we organize it as such. And now from this, let's extract the predictions that are positive. Now we call this recalled, because out of all the positive images, how many did the test actually predict them to be positive? How many did the test recall? In terms of the table, we say that the denominator is TP, the true positives, plus the false negatives. Remember, this row is all the positive, the actual Lambos. So we have all the actual Lambos, the denominator. And then the numerator is just true positive. How many of those we recalled? Putting this together into an equation, we have the following. And this is what's known as recall. So now we have three parameters: recall, accuracy, and precision. For reference, I'm going to bring back this notation for the rows, actual positive, actual negative, and I'm going to bring back this notation for the columns, and then obviously the S. Seeing it like this, we can say that another way of recall is saying the true positive or the actual positive, and precision as true positive or the predicted positive. So this is one way to kind of differentiate. If you're confused between recall and precision, this is one way to differentiate the two. One is all the positives over the predictions, and one is all the positives over the actual. So recall is all the actual positives that existed. How many did the model pick them up, did recall? But the precision is where in the model, out of all the predictions we made, positive predictions we made, how many of those positive predictions were correct? How precise was our model? And from here, we can generate three more metrics where we have specificity, F1 score, and prevalence. Now, specificity is actually a lot like recall. You can think of it as like the negative complement, whereas recall is the true positives over all the positives. The specificity is the true negative over all the negative. So it's basically saying that out of all the negatives, how many did our model pick up as negatives, okay? And moving on to prevalence. Prevalence is basically, you can say it's like accuracy, but where accuracy just focuses on all the correct over all the predictions, prevalence just focuses on just all the positives over all the predictions. You can think of prevalence is more useful when you're trying to see how balanced our data set is. If our prevalence is too high, typically you want prevalence around like 50%, because if it's too high, then that means you have too many positives. So it's not really a balanced set. Okay. Speaking of balance, let's move on to F1 score. F1 score, so this equation you see right here is what we call a harmonic mean. And harmonic mean is something you take when you're trying to kind of average rates. Obviously, recall and precision are what you consider rates. Their values are typically between 0 and 1. So this equation is like a harmonic mean between precision and recall. So basically what you're doing is F1 score is you're taking a balance of precision and recall. You can say it is like accuracy, and you'll see that in a bit, okay? And that brings us to our next point. So scenario A is disease. We have 4 possible outcomes. We can say either the patient has the disease and he's correctly identified, the patient has a disease, he's incorrectly identified, the patient doesn't have disease, he's correctly identified, and the patient doesn't have disease and incorrectly identified. Now, right away we can see that our true positive is the top row. If you classify the disease as a positive, in this case we truly identified that, so it's a true positive. This is of utmost importance. We want to pick this up. Okay. Next up, we have a true negative. It is no disease and it is correctly identified. This is probably the best case scenario. This is what we always want. Somebody to have no disease, and they indeed have no disease. Okay? After that, we have a false positive. Now, this is a bad situation. It's a false alarm. We don't want this. But it is not as bad as this, a false negative, where the patient has a disease and we don't pick it up. So he could end up being dead. So that is not a good scenario. So out of all of these, clearly we can see that the worst scenario is this scenario, the false negative. So a good metric for this test would probably be something that picks up a false negative. And one metric obviously is recall, because we can see how false negative is in the denominator. So in this case, a low recall would mean we have a lot of false negatives, and a high recall would mean we have no false negatives. So again, this is a good predictor in this scenario. Now, instead of disease, let's say we focus on drug testing, where in this scenario, we're trying to test if a person is on drugs or not, and if they are, then obviously they will go to jail. So in this scenario, probably the worst case scenario in terms of for that person would be a situation of this, where he has no drug and he's incorrectly identified. So he's not on drugs, he's gonna go to jail. So that is the worst case scenario. He's probably gonna spend his life crying. And in a situation like this, we wanna use a metric that picks up on false, just like as in the previous scenario, it picked up on false negative. Now we want a scenario that picks up on false positive. The metric we can use is specificity, because now instead of on false negatives, we're picking up on false positives. Our next scenario is spam email, where now we have the following 4 cases similar to our previous scenarios, and we can similarly identify the true positive, false negative, true negative, and false positive. Now in this scenario, for the true positive and the false positive, the spam block will pick up as spam here correctly, but incorrectly pick up as spam here. So in both these cases, the spam blocker will throw the email into trash. Now these 2 scenarios aren't that bad because they won't go to trash. This scenario might be annoying because you don't want spam in your regular email, but they're bearable because at least you still have them, worst case, for reference. But out of these 2, the one that is worse will probably be the no spam that is incorrectly identified and thrown into the trash. So basically, in this case, you have regular email, but the spam blocker identified as spam. So it could be an important email from some person, but it tweeted as trash, and you never even know. So in your model, your spam blocker model, the metric you want to use is the one that isolates false positives. So in this case, you probably use a precision, because precision isolates false positives. The higher the precision, the less false positives you have. Now, what would be the case for using accuracy and F1 score in our binary scenario of Lambos and Rorys? Well, if we bring back the table, the 4 possible outcomes, let's say for a moment that these 4 areas relative to each other represent the actual scale of these proportions in the data set. Then in this case, these areas are pretty much equal. So we can say this is a pretty balanced data set. And accuracy is pretty well when all those other, like accuracy as well when you don't care about picking whether true positive, false positive, or any of these over the other, where all their cost is pretty similar. And your areas are equal and you have a balanced data set. That's when you want to use accuracy. But F1 score, you want to use it when neither of these are important. Their cost is all the same, but the dataset is imbalanced. It could sway up, it could sway left, it could sway down, or it could sway extremely to the right. It is imbalanced. Revisiting our model, now if we input the images, instead of classifying just Lambos and Rorys, let's say we classify 4 more classes. A Bugatti score of 2, a McLaren score of 3, a Lexus score of 4, and an Aston Martin a score of 5. Going back to our contingency table, seeing that the rows were the actual and the columns were the predicted. In our case of a binary, we were able to sort it as such. But now, let's say we want to include the Bugatti. Now it becomes a 3x3. For a McLaren, it becomes a 4x4. And now, including the rest, it becomes a 6x6. Now, what this is actually known as a confusion matrix. It's given such a name because it is displaying all the outcomes of the model, all the predictions, even the ones where it is confused, which are quite many of them, as you'll see. So to put this into an example, let's say we had 6,000 total images where we divided 1,000 for each possible class. So the rows total to 1,000. And after running the model, we came out with the following results. To get the accuracy in a multi-class situation, ideally what you do is all the predictions, of course, cover the total table, but the correct predictions just cover the diagonals. Actual Lambo, correctly predicted as Lambo. Actual Rari, correctly predicted as Rari. Actual Bugatti, correctly predicted as Bugatti, and so on and so forth. Now, given this, right away you can see that accuracy will typically be large if the values in these diagonals are much larger than the remaining. So, to kind of better see this, if we focus on all the actual Bugattis, we see that only 231 of them it actually predicted as Bugattis. This is actually quite low. It should be much, much higher. So this number will probably bring down the accuracy. Whereas if you look at these two cases for the McLaren and the Aston Martin, a lot of them it predicted correctly at Aston Martin, where virtually none it incorrectly predicted. McLaren. Again, a lot of them it predicted as Aston Martin, where virtually none it predicted as something else. So these two cases are going to bring up the accuracy. Now, what about the other metrics? How will they apply to this multi-class situation? Well, for a moment, we can just focus on the top four and ignore F1 score, because if you get recall and precision, you can get F1 score. Now, the idea is, as long as you identify what your positives are and what your negatives are, then you can calculate these metrics. So you have to identify what is your positive and what is your negative. Basically, you're trying to force a binary setting into a non-binary situation. You have 6 possible outcomes, but you want to define it as 2. So it's simple. It depends on where your focus is. If your focus was Lamborghini, then bringing back our 2x2 case for reference, we can say that the positives is just a 0 and the negatives are the ones where it's not a 0. So this whole table can emulate the 2x2 case as such. This outcome is a true positive. All these outcomes are the true negative. This is false negative, this is false positive. And based on this logic, we can calculate for other cases when our focus shifts. For example, if our focus shifts to Ferrari, for our positive to be Ferrari, then the positive becomes a 1 and our outcomes shift as such. Similar thing for Bugatti, and so on and so forth.